one of the previous tutorials, I was showing how you can calculate the conductance of like a real-life CAD system. So here we can see a perforated radio frequency liner. And the question was that instead of modeling every single hole, which results in a big number of facets, like here you can see it's about 16,000, would it be possible to replace this structure with a single facet, which is two-sided or one-sided, and it would greatly simplify the geometry? Would it be possible to define different physics on the outer side as from the inner side? And can you apply a temperature gradient? So let's see a simple example for that. And instead of working on this geometry where I would have to make two cuts and align it with the exact same structure, I will show an easier example, but later I will show how you can treat the harder cases as well. So here, the only thing I modified is I was like cutting off everything that's not part of the system that I want to simplify. Here you can see that we've got like an RF liner. It's got some wall thickness. If I turn on the volume view, then and turn on the texture, you can see that there are some holes. Maybe I will just rotate the lighting so you can see it better. And the idea is that since I was modeling exactly one period, if I'm looking from the side, you can see that you've got about 3 holes. Then I could replace this with a single cylinder, but I would like the physics to behave more or less the same as with the full structure. So what I will do is first, I have created 2 profiles here. I will just check what the pressure on them is. So you can see that it's about like 6 to the minus 3 and 3.5 to the minus 3 millibars. And I will just simply note down those values. So 0.00607 and 0.003517. Don't forget that Monte Carlo simulations are not infinitely precise. And also we can see the profile plotter. So you've got the higher pressure facet in the middle, that's the red curve, and the lower pressure, which is the outside. And you can see that there is some asymmetry here because there are like more holes a little bit in the middle. You can see that on the top you've got 3 holes. You've got slightly lower pressure on the outside, but apart from that, it's more or less like a flat profile. So the idea is that now we will replace it, and then we will check the new profiles, and if we did everything correctly, we would get the same result. So before we go on and delete everything, I will actually construct the part which will replace it first. So for that, I would go to this create shape command. I will create a circle. Usually I use 36 sides because it's a nice number. It means that every side covers 10 degrees. And I would like a circle to be created at this point. So for that, I can like select a facet and I click on facet center, and it calculates that this is at the minus 8.25 centimeter coordinate. And the y coordinate is a very small number. This is because it's trying to get the center by calculating like all sides of the facet. So obviously this should be 0. I will just replace it, otherwise you get tiny rounding errors. Now 10 to the minus 9 doesn't count that much. And basically we're ready, so I will just create diameter 1 circle. And this is too small. And what I will do is I will just take the scale command, and either I have already known what I would like to create, so I could have entered the diameter directly, but I like this mode. I just put like 1.1, and then I can like scale up the facet. Now one thing I did wrongly, I will just delete this facet, create it again. That basically when I'm doing scaling, I have to ask to take this point as a center. So I was just clicking on get selected center of the facet. So now it works as it should. I will just go in the front view, and here I keep increasing the circle until it's more or less the average. So I will go exactly in the front, And now it's slightly too big, so I will just make it a tiny bit smaller. It doesn't really matter, but we will use it for some area calculations. So I like it if it's nicely between the two. So this is the cylinder that will replace the original structure. So right now I've got already one circle. Now I could do an extrusion. There is a trick which I will show, but maybe it's just a side step. So I will actually move this facet that I just created away from the system, so like 15 centimeters in the x direction. And if I'm looking from the side, it doesn't matter that I moved it. Now I can create a structure and I can work on it independent of the rest of the system. So what I will do is now I will keep moving this facet. Okay, this is the wrong direction. So I just made a copy of it. I use the copy facet button. And I will just have to find the correct place. Now, this is more or less the correct place. Another thing that I could have done is that actually I could have said that I want this to be the plane where it snaps to. So I will go to facet mirror. I will get the plane of this facet. I select this one and I ask it to be projected, and then it's automatically there. So I'm trying to not take advantage of the round coordinates and the orientation of the system. This is something that you can use even if your system is sideways. So now we have two facets so far. Let's connect them. What we will do is I will just use this transition between the two, and it automatically completes. So now I've got a cylinder. Apart from that, I could have used, there is another command, it's called extrude. If you know how long it should be, you can make an extrusion and then you can construct a pipe anyway. So now, since it's not exactly the same position, it's very easy to make selections. I can just remove the side caps. I will just delete them. All right. So the question is that you have to do calculations how transparent this should be to correspond to this. So now if you're using a CAD program, you can just automatically select the inner side, and your CAD program will tell you automatically its area. Then you can compare it to a cylinder, and then you exactly know the surface ratio between the complete cylinder and the whole cylinder. Since I don't want this tutorial to be dependent of an external program, I will do the calculation in Molflow. In advance, I'm telling that this takes some time, but the second time you do it, it will be much faster. So I need a calculator, and Molflow has a formula editor which you can also use as a calculator. So I already deleted the capping facets, so I will just select everything. And I will save it as a selection so I can recall it later. I will just call it replacement. All right, if you don't know selections, like in the selection menu, I just use the memorize command. Now you can call the select, or you can also press Alt-1 and then it's automatically calculated. So right now we can see that the area is about 156 square centimeter. I will just copy this number here and I will call it like mockup area. So now I would like to compare it to my system. For that I go to front view, and here I take, basically I'm pressing the Alt key, and when you're pressing the Alt key you can select facets in a circle. Either you start your circle exactly from the center, or if you press the space key then you can remove the center point. So I will just put it very nicely to the center, and with this trick I can carefully select the inner side. Just be careful that I have to deselect this. So I will call it inner side. I will copy its area, 93 square centimeters. I will call it inner area. And I will do the outer side. Now for the outer side, we can learn a new trick. So here I will draw a circle. And what I want to deselect the center of the circle. Now the problem is that if I'm drawing a deselection like this, everything will be deselected. Otherwise, the sides of the hole will remain selected. So there is a trick that you can use. Either you draw more circles and you just remove parts of them, but it's tiresome. But there is a way to very quickly deselect the inner sides. So I will just select everything again. I will deselect the inner part. And now I switch to vertex selection mode. And vertex selection mode allows you to mark corners of the facets. So now I do one more selection and I have selected all the inner facets. Now I go back to facet selection mode and I press caps lock. And since I pressed caps lock, you can see that on the lower left corner it writes that select facets only with selected vertex. Now what it does, if for example I'm trying to add to the selection, nothing happens because these facets are not sharing sides with the vertices I have selected. So what I can do is right now I ask to deselect, I draw everything, and you can see that he removes only those facets from the selection which had a vertex shared with them. So right now I've got the outer side nicely selected, even if I had to go through a size step. And I will just save this selection as outer side. Caps lock is still on outer side. Okay, the goal obviously was to copy the area, outer area. And now we will see what's the average area. So you've got the outer area, the inner area, or mockup is in between the two. So you are interested in how much the average of this 93.356.439 and 105.299116. So this is the average area, and you are interested how it relates to the full cylinder, which is 156.459.886. Okay, so as you can see, maybe later you will get an option to refer to previous formulas. For the moment, you have to manually copy values. So let's call it area ratio. And you could think that at this point, if you give an opacity of 0.6348 and make this two-sided, then you've got the equivalent. Just as a reminder, you see that the normal vectors are pointing inside, or you can swap them inside or outside. But by default, if your facets are one-sided, it doesn't catch particles from its opposite side. So that's why we made it two-sided. At this point, I will just save the geometry. So I will just, for example, call it mockup ready. And the problem is that when you're doing a simulation, and we just launch the simulation, it's a little bit hard to catch one of these events, but probably we will be able to see a collision. Yes, here you can see that the particles can hit the side of the hole, and then it can actually turn back and fly back to the system. So it's not so easy that if your particle is hitting a hole, then it's automatically going through it. You have to take into account that these holes have sides, and the sides can turn back the particles. So how do you take that into account? For that, you will do the modeling of one single hole and try to get its transition probability. So I have selected the top hole, and the reason for that is that you can see that these sides, they are curved. So if you would like to do a transmission probability calculation, you would need to do a curved target facet and a curved inner facet. It's possible, but first we will see how we can simplify our life, and for that we will simply select the top hole. Now I will manually deselect everything that I will just use the vertex selection mode, so I have selected all the vertices. And now, with caps lock on, I can deselect the neighbors. I actually made a mistake. I will just select everything again, and instead of the caps lock mode, I will deselect the neighbors manually. Okay, it took some time, but finally it's now ready. And we will make a copy of this hole, so I will just move it towards the Z-wire direction by 10 centimeters. Don't forget to click copy. And here I got a single hole. So what I could do is I will create a facet on the lower side. For that I select every vertex. I say vertex create facet with a convex hull. And I select another one. Okay, so the idea is that one of them will desorb, the other will catch, and we will see how many of them go through as opposed to hitting the side. However, there is a problem. You can see that these facets are purple, which means that they are not in the same plane. And this is expected because this is a curved surface. So in the future versions, you would have a triangulate command, which can break up this curved facet to smaller triangles and still use it normally. However, we will just do a small simplification. You can see that this is almost a flat surface. So I will just take these vertices and modify the coordinates. So you can see that their y-coordinate changes slightly. And I will just, the largest y-coordinate is 3.4, the smallest is 3.39 here. So I will just take the average 3.395. Okay, so I will do the same with the bottom facet. And here the average coordinate should be 3.14, and I will just use, I can see 0.05, let's say 0.7. Okay, so we made a tiny bit of modification to the geometry, but the transmission probability will be practically the same. And don't forget that in the future version, you will be able to issue a triangulate command, and then you don't have to do any modifications at all. Exported one single hole, I have to set it up to simulate the transmission probability. So I will just check the sides. I want this side to actually emit particles upwards, so I will swap its normal. I will set up a desorption with any unit, let's say 1 millibar times liter per second, and I want particles to be able to come back to where they came from, so I set a sticking of 1. It means that the particle, if it rebounds, then it will disappear, but if it makes it to the other side, then the sticking factor should also be 1. So basically, I start a simulation, I just make the dots a little bit larger. And you can see, I stop it, that some particles make it to the other side, but some of them, they make a reflection on the side of the hole, and then they return to where they came from. So either transmission or return to the origin. To see the ratio of the two, I need the numbers of the facets. So this is facet 3469, and this is facet 3468. So I want to see those particles that absorbed on facet 3469 and divided by everything that's desorbing at 3468. You have a small cheat sheet here, so you can see that AN, so the absorption on facet number N or DN, are valid variables. I keep it running for a little bit, and I can see that as the simulation is running, this value is being updated. But let it run during that, and I can already write my formulas. So it means that I have seen that the ratio of the areas is about 0.63. So let's first calculate the transparency. So the transparency is the probability that you hit a hole, which means that I subtract the area of the wall from the total area. So this would be like the ratio of the holes. And once my particle gets into a hole, I have to give only 77% that it will actually cross it. And that's why I get a transparency about 0.28169. Since I cannot refer to other formulas in this version yet, I will just manually copy this for you. Oh yeah, I missed the decimal. So yeah, basically this will be the opacity. And once again, this was the transparency. So now that we have this, I can assign this opacity to the wall. And I will just put 0.718831. So try to test what we did. I will just delete the original geometry. Before that, I will just do one save. And then I will move back to its place, and then we can test it. So I will just move it. Okay, right now it's at position. So let's check if we did our calculations correctly. You can see that the texture profile is similar to what we had before. Let's see the profile plotter. We've got two curves as before. And finally, let's select the two profile facets. One in the inside and one in the outside. Let's check the pressure on them. And then, here is the notes that I've taken at the beginning of this tutorial. Okay, I'll do some updates. So I did the comparison. I was actually importing the two geometries to be next to each other. So here you can see the original geometry, and here the one which is simplified. The only thing is that I slightly updated the values calculated before here in the formula editor because of the issue before. When I calculated the transmission ratio of the hole, I accidentally selected uniform desorption as opposed to the cosine desorption, which should be the default for vacuum systems. So, if you look at the texture, you can see that the colors are basically the same. Now, if you look at the two profiles, you can see that the outer pressure is pretty much the same, and the inner pressure is slightly higher in the original geometry. How much higher? You can see that it's like 5.24 in the original and 5.36 in the new one. So why is this? There are several reasons. So first of all, here we have used only 36 sides, so this is not a perfect circle. This geometry was slightly more detailed. Also, I was only using 3 periods, so probably the cutting is not perfect. If I used more periods, it would be a better approximation. And finally, I also realized that when I go to the front view, you can see that I was taking the average of the two diameters, and then in my calculation I was taking the average of the two areas. But actually the areas scale with the square of the diameter, so this averaging is also bringing a little bit of uncertainty. Still, in the end, we have reduced the geometry, so instead of 3 3,400 facets in the original one. We could get away with only 133, and the difference is only very slight. So once again, I will just select the profiles, and you can see that the outer pressure is the same, the inner pressure is slightly different, the opacity was not perfectly calculated. Now I will go back and actually show you a few more difficult cases. So here I had an RF finger, which we are not going to solve this time. Here you can see how the fingers were. And I was recreating circles, and using the scale command I was trying to follow the shape. So if you look from the side, the diameters are matching the original shape. Here I was calculating the area ratio, and then I was doing the simulation of one single hole. And here one single hole, when I select this option, here I cannot modify the geometry, I have to use the triangulation command. So this is what will be available in the next version. If I turn on the lines, you can see that the simulation is just like before. So I'm desorbing from one side and the other is sticking, so I can still calculate the transmission probability in this irregular shaped wall. I'm going back to the original tutorial, so I will just, a second, I will just open the solution. And there are a few special cases to treat. So right now the physics is exactly the same on the inside and on the outside, but you might have some occasions when you would like to change. For example, the sticking factor is different on the inside than on the outside, or you've got like a coating on the outside that changes the outgassing. So right now, if I select, actually, like if I go to the smart selection and click on this, you can select the shape instantly. Turning on the normal vectors, you can see that these facets are facing outside. It doesn't really matter because they are two-sided, but if it like different physics on the inside and on the outside, I will just switch it to one-sided. And I will make a copy which will be slightly smaller. So I will use the scale command. Here the axis of scaling is the z-axis, but I wouldn't like to use it as an invariant point because I will be taking advantage of the geometry. So what you could do is you could create a facet. For example, I could select everything. I could deselect these vertices. Okay, I made a mistake. Let's try it again. Okay, I will just use vertex create from selected convex hull, so I could select a new facet, and then I could get the center of this facet as the invariant point. So in this case, I will just scale the facet, so I will just okay, and I will make uniform scaling, and I will make it really slightly smaller. I made a copy. Now apparently nothing happened, but if you really zoom in, you can see that now there are two walls, one on the outside, and we have just created the inside. I will swap the normal vectors, and now we've got two different walls, one on the outside and one on the inside. And if you're using smart selection, you can select the whole outside or the inside. I have to reanalyze the geometry because I have modified it, so you can select the inner or the outer walls. One tiny thing is that because we did the scaling with the invariant point, which was here, right now the inner walls coordinates are not exactly at the same place as they should be. I will just correct those. So you can see that most of the coordinates are 15.85, and you've got a few which were scaled down. I will just correct those, minus 15.85, and the geometry is fixed again. And now at this point, you have to understand why once on these facets were introduced. So these facets are catching from the outside with a probability of 75%. But if the particle goes through them, they will go through the inner side as well because they are facing inwards. And since they are one-sided facets, they don't reflect from the back. So particles can still go through them exactly as if it was a double-sided facet. But here, for example, I can specify a sticking factor of 0.1 for the inner side of the geometry, but not the outer side. I can just run the simulation to check if everything is working. And you can see that, for example, I could add some outgassing to the outer wall. I just add a small outgassing. And now the pressure is higher outside. Okay, so I will just save this. Solved. Double-walled. And the question was, how could we apply some physics gradient, for example, a temperature gradient on that? And what we want to do is to basically slice it up, and then we can assign a different parameter for each of the slices. So for that, what I will do is I will create cutting planes. So what I need to do is I will just select 3 vertices. I will create a facet out of them. This is a simple triangle, but it doesn't matter because we will only use it to define as a cutting plane. I will just turn it around, and let's say you want to cut it at every 1 centimeter. So I will just use the move command. I will move towards the normal vector, and the direction should be 1 centimeter. Don't forget to click on the copy facet instead of the move facet, and then basically I can define my cutting planes. All right. So how do I do the actual cuts? So when you choose the split command, then you can define by clicking get selected to make this the cutting plane. The problem is that we would have like the cylinder selected, and we would always have to click away, lose the selection, get one of these cutting planes by a lot of clicking, and then select it again because the cutting deselected. So what I will do is I will just select once again the cylinder that we're trying to cut. And instead of facet plane, I will use the free selected vertex mode. Just either to select vertices, you either click on this vertex selection mode. Now I've got like a V letter next to my cursor. Or you can press the tab key, and then it writes tab key down, facet vertex selection mode swept. So this is easier for me because in this case, I will just first select the first cutting plane. It's relatively easy. I will ask it to split. I turn off the normals. Now I have seen that there is a splitting already happened. And now I don't have to leave the selection. I just press the tab key. I select the next splitting plane and click split again. What you could also do is you could manually write the equation of the plane, and here the offset from the xy plane would always decrease by 1 centimeter, but I don't like that because here I would take advantage of the orientation of my geometry, and you could have an arbitrary geometry. So it will take a little bit of time, but I will very quickly just do all the splittings. Since these triangles are in the middle, if I go for a side view, I could just make a very quick selection, and then I could finish my splitting. So right now, we don't need these splitting planes anymore, so I will just delete them. Okay, facet, delete, everything is left. And now I still got the double walled facets, but I can control them one by one. So for example, on this part, the temperature is room temperature. On the next one, I could put 250 degrees, and I will decrease it by about 30, so 220. 190. $160. So yeah, it would be maybe better if there would be an automatic way to create a gradient, but it's very hard to do when your geometry is polygonized and you don't have a knowledge of the actual shape behind it. All right, so the last one, let's make it 70 Kelvin. If I run the simulation again, now you can see that there is a temperature gradient. I will just turn off the outgassing because it will create more harm than good. So I will just make sure that this is the only outgassing facet. I invert the selection, just a second, and I disable the outgassing. Okay, and right now you can see that if I go to the texture scaling, the pressure is increasing to the left side, to the hot side. However, the density, which I have to change the auto scaling a little bit, just a second. I'm trying to find the good values, so 3.8, let's make it 3, still I need a little bit more, 2. Okay, so here this is a good view. You can see that the density increases to the cold side because particles slow down, and the impingement rate is all uniform. It doesn't depend on temperature. So here we have already created like a pressure-dependent system relatively easily. So thank you for your attention. Obviously, when you have real shapes, you have to be a bit more creative to create the mock-up, so cylinder was easier to handle. But still, you replaced 16,000 facets with a couple of hundred. It's still 600, and before slicing the cylinder, it was significantly less, just a few hundred.